And given a subgroup age of G, I forgot to say this is denoted with this smaller equal relation. And given a subgroup age of G and an element X in G, the left coset of age with respect to X is the set, it's denoted X dot age, or just X age. This is the set of all expressions of the form X times Y, such that Y is an element in H. Okay? So the coset, you can think of it as a shift of the subgroup. So, example, we take G to be the set of the real plane. This is the set of tuples X, Y. Maybe we do it A, B, such that A and B are real numbers. And we have a natural operation of adding two vectors, two elements here. Let's say A prime, B prime. This is defined to be A plus A prime, B plus B prime. And the neutral element is a 0, 0. So this is a group, it's very easy to check. And as a subgroup, we take H, just pick for I guess, say do M and alpha, two real numbers. I can consider H to be the set of solutions X comma Y, or maybe we said AB, such that B is equal to MA plus alpha. So this set of solution is a line in the, for a given M and alpha, H is simply a line that passes, actually alpha needs to be 0. I'm sorry. So it has to be a line that passes through the origin, because for H to be a subgroup, it needs to contain the neutral element. So the picture is like this. This is H. And H is indeed a subgroup. Here, by the way, I mean, if this is alpha, then M is going to be, I think, tangents alpha. This, yeah, okay, alpha is not used. So H is a subgroup of G. And it's very easy to see, because if you take two elements, if you take two elements in H, say A, B, and A prime, B prime, you add them two together, you just get another guy that satisfies. I mean, then you know that you have this equation satisfied, and you have also the other equation satisfied. And so when you sum the equations, you get that B plus B prime is equal to M A plus A prime. And this means, this is equivalent to say that A plus A prime, B plus B prime is an element in H, right? An element in H is something that satisfies this equation. Is this okay? Is it clear why H is a subgroup of R2? Okay, and now if I do the cosets, now I pick P to be, or maybe we do it capital X, to be an element in R2. And I want to consider what is the coset X of H with respect to X. But note that we are, for this group G, we are using additive notation, right? Instead of multiplicative notation that we did in the general case. So with additive notation, the coset of H with respect to X is denoted X plus H. And what is it? X plus H. It's, let's say that X is some S comma T. Then this is all S comma T plus A comma B, such that A comma B is an element in R2, in H. But if you look at it, this is just, of course, I can write it simply as S plus A T plus B, such that A comma B is in H. But for A comma B to be in H, I know what has to happen. I need that B is equal to MA. Right? This is the condition to be in H.
S equals MT, because D equals MA is definition of A and B being partial. So
yeah, no, it's S comma T was picked not in H. S comma T is an element in the ambient group in G.
Yeah. Yes, well, I understand what
X is S comma T. x is s comma t. Remember, a coset of h is you pick an element in the ambient group, in the big group, and then you take the coset of the subgroup with respect to this element. So I pick a general element in the group. This is just a point, s comma t, with no restriction. And now I look at the coset of this element with respect to the, or the coset of h with respect to this element. What is it? Again, I write plus instead of, I mean, in the general case, we wrote instead of plus, we wrote a multiplication. But this is just the binary operation of the group. The binary operation here is better written in additive notation. And x plus h, by definition, is you take x and you take all the x operation with an element in h. Right? This I write again here in purple. xh in the multiplicative notation, it was all the x comma x operation h or h in h. Right? So if I do this, for our case, this is x operation a comma b, where a comma b is in h. Right? This a comma b now takes the role of h in the purple part. Is this clear?
It's clear, yeah.
Okay. So now, but what is it? We know what it is to. I mean, I have this vector. Say it is like this. This is x. X is s comma t. I can picture it as a vector, and this is h. And now I need to add every vector in h. I need to add to x. How do you add two vectors in the xy plane? You do a parallelogram. So I picture a parallelogram. It is fortunately not very precise, but this, I hope you get the idea. And the corner of the parallelogram is the resulting vector of, and I can do this parallelogram for all the arrow, I mean all the points of h where I consider them as arrows. So what I get is this blue line. The collection of all points of, so this blue line is going to be x plus h.
Yeah, could you just scroll a tiny bit? Right. So my question is, in the case of x belonging to h as well, you don't have a coset at all. You have, I mean, or
you have a coset. It's going to be h.
So h is a coset of h.
I mean, our terminology was a coset of h with respect to x. So coset is always a coset is like a shift. That's what this is what I'm trying to demonstrate in this example, that a coset is like a shift of the original subgroup,
right,
by an element.
Right.
You see, or instead of a shift, you can say translation. This, I translated x plus h is a translation of h, I mean, in the direction of x.
Right.
Okay. And what I did here for X was general, right? I didn't assume anything on X, so you can do it for any element in any vector. And so what you get is a collection. I mean, you do it for all vectors. You get a collection of lines that covers all the plane, right? Okay.
Okay.
Yeah.
I have a question, but I don't know what's coming next, so maybe it's not the right time to ask it. Okay, I'll try.
Yeah.
If we look at a different model, that would be a circle. Well, okay, more exactly, the operation, we take the plane, the usual plane, R square.
Yes.
And we, instead of having, like let's say you have, but we need to, right now, actually, it's one operation that would be both scaling and rotating.
Let me give you an example. I think that is maybe
Okay.
it's something similar to what you had in mind. I take the circle. The circle is denoted as S1.
Yeah.
I treat it as a subset of the complex numbers.
Okay.
Okay. And now I view the plane as the complex plane instead of the.
Yeah. Very nice.
And this is a subgroup with respect to complex multiplication. Because complex multiplication, I mean, if I have Z and Z prime in the circle, then I can just multiply them. The norm, the complex norm of Z times Z prime is going to be equal to the complex norm of Z times the complex norm of Z prime. Complex norm is simply the distance from the origin. Okay. And if they are on S1 on the circle, I mean the unit circle, the distance of every point in the unit circle from the origin is 1. So this is going to be 1 times 1, which is 1. So you see that Z times Z prime is also of distance 1 from the origin, and hence it's again an element in the circle. And in fact, what happens if Z is this vector and Z prime is this vector, then you have two angles, say alpha and alpha prime. And the multiplication of Z and Z prime is simply adding these two angles. So this is Z times Z prime. The resulting angle is alpha plus alpha prime. And so you see, I mean, this group is written multiplicatively, but what is really going on is addition of angles. Okay. Now, within this group, I have the group of nth roots of unity. This was called MNC. This is the set of solutions to the equation, the complex equation, Z to the N equals 1. Okay, so if you take N equals 3, for example, what you do is you divide the circle into 3 equal parts. So it would be like this, I guess. And you call these guys Z0, Z1, and Z2. This is M3C. And it is a subgroup. It is a subgroup of S1.
Yeah.
Right? Now I can consider I take an element in S1, let's say X, and I consider the coset of X with respect to M3C. What is it? This is a coset. This M3C, I mean, I will write as H, okay? But this is by definition X times Z, where Z is an element in the subgroup in H, in M3C. But what does it mean? We said we know how to do how to interpret geometrically a multiplication of complex numbers, especially on the circle. On the circle is just adding the two angles. So this coset X times M3C, it's, first of all, we know that this can be a set of at most 3 elements, because M3C has 3 elements. I cannot get more than 3 elements. But in fact, it's just a shift. So the coset will be, I mean, let's say that this is alpha. Then I shift Z0, Z1, and Z2 by alpha. So it will be, now this is going to be X times Z0 is simply X, right? Because I shifted Z0 by alpha. Z0 has angle 0. So I get this vector. Then I shift Z1 by alpha, so I get this vector. This is X Z1. And then I shift Z2 by alpha, I get this vector. X Z2. Okay, so you see the coset of the subgroup M3C with respect to some general element X is just rotating, it's just shifting. So these cosets are just shifts of the group.
Yeah, okay. Yes, understood. I mean, okay, maybe someone has a question. My question was more, instead of multiplying that was actually to take the other variable sign, which was R, instead of the alpha, the scaling, so still multiplication by a
Wait,
complex number.
what is your group? R with respect to plus? R2 with respect to plus?
Basically, it's you still take the group, which is the unit circle, so S1.
Yes.
And you still have this complex multiplication, but you multiply by a series of numbers that are by real numbers. So you just scale the tree, the circle. That would create cosets too, right?
Yeah. Okay. So your example, that's maybe it's good also to picture it. So
it's not a subgroup.
no, we can do.
No, it's a coset. Yeah.
Okay. So
the group is the circle, then
the group is
the circle will not be a subgroup.
Ah, right.
no. So what you can make it work, but you need to be a bit more careful. You can look at G to be the complex numbers without the origin.
Right.
Without, okay.
Right, because that was going to be my question precisely. That's what I was trying to get.
And then this is a group with respect to complex multiplication.
Okay.
Okay. And now S1 is a subgroup,
Right.
is a subgroup of G
Yeah.
with respect to multiplication.
Mhm.
Now I take an element X, so this is H. I take an element X in C minus the origin.
Right.
And I look at the coset XH. XH is like S1. And now you need to understand what does it mean to do multiplication of complex numbers geometrically. If you want to, but doing multiplication of complex numbers geometrically is you multiply the radius and you add the angles. Okay, so if X is like this, then I mean, since I do X times S1 for all S1,
Yeah.
then let's say the radius of X is bigger than 1, then I get whatever this R. Then I take the unit circle and I stretch it by R.
Right.
And that's my
Exactly.
that's my coset.
So that's a coset, but it's not a group, right? Because it doesn't have a neutral element.
It's not a group. No, it has a neutral. It has a neutral element. Ah, yeah, it doesn't because it's not one. It's not a group for several reasons.
Right.
Yes. Also, when you multiply two elements here, this is like XS1.
Right.
But the radius here is like
Right.
it's basically actually it's R. I drew it wrongly. And now I take the unit circle, the circle with radius R, you see. And this is not closed under multiplication.
Right.
Because you take two elements, you multiply them, the radius is being multiplied. So you don't get a new element on this circle.
Right, yeah.
But nevertheless, I took it for all X. I can cover all the plane with these cosets.
Yeah.
Okay. So, and this is really my next proposition.
So just before we go, yeah, so you could cover all the plane except the zero. That's what prompted me to bring this example.
But I didn't start with zero.
Right. So you can't set zero.
Okay.
So it's,
if I included zero, then it wouldn't be a group with respect to multiplication.
Begin with. Yeah. Okay. Cool. Sorry. Yeah.
Okay. So to really pin down the phenomena, we have the next proposition. For a group G and a subgroup H, the set of cosets of all cosets I write it like this: XH such that X is in G. Or I guess maybe a notation you are more used to is like this. Okay, let me just, I'll write the two notations. Usually it's more handy to write it like this: X in G, but this notation really means just XH such that X is in G. Okay, so just to abbreviate this notation, we have this one, and I claim this is a set of sets, right? It's a set of sets, or a set of subsets of G, and I claim that this forms a partition of G, i.e., what is a partition? A partition, it means that first, the union of all the guys in this set, that is the union of all x age such that x is in G. This is a union of subsets of G, and I claim that the union is G itself. That is, this collection of subset covers G. And the second condition for being a partition is that if x age and y age are two elements in the candidate for being a partition, then either x age is equal to y age, or x age intersection y age is the empty set. Okay, so in words, in plain words, it means that let's write it like this: if x, y in G then either x age is equal to y age, or x age intersection y age is disjoint, is the empty set. And so a partition in words is a collection of subsets of the ambient set that covers the ambient set, so that the union of all the subsets is the big set, and every two sets in this collection are disjoint, or I mean either equal or disjoint. Okay. Now note that there is a lot of repetition when I write it like this: x age, or like this, all the x age where x is in G. This is a collection of subsets of G, but it has a lot of repetitions. We actually, I'm not sure if we proved it last time, but well, okay, we can leave it later. But we, for example, we did see that if, for example, x is in age, then x age is simply equal to age, because I mean this is very easy manipulation. I mean x age, this coset of age with respect to x, is x age in age, but I can write it simply as x times x minus 1 age, where age in age, or yeah, and this is simply it's all the age such that age. You see, it's like for example, if x is the unit element, the neutral element 1, then clearly this is age. So the coset x age may be equal to age. I mean, if X is in H, there will be many cosets XH that are simply equal to H. And all the cosets, with respect to elements in H are H again. So in other words, here you have a lot of repetitions. But remember, a set, we consider a set as something that ignores repetition. So it's handy to write it like this: XH or X is in G, and do not worry about repetition. And because I write it as a set, it means that I omit all the repetitions. Okay, so back to the proposition, and let's see how it goes. So first, we have condition A, right? Condition A, we want to show that the union of all XH is G. The X in G. That's very easy because for one, for any one is always an element in H. So X times one, so for any X in G, X times one belongs to the coset XH, right? So the union of all XH is already G, right? Because I took a general element X, and I can express it as an element in some coset, namely the coset of H with respect to X. And this means that I can get all the elements of G as elements as belonging to at least one of the cosets. Is this clear? This should be the easy part, but I don't want to move on with. So, okay, so to show equality of sets, we need to show double inclusion. But one inclusion is obvious. This is obvious because it's a union of subsets of G. Okay, a union of subsets of anything is a subset of this thing. Okay, so it's a union of subsets of G, so it must be a subset of G. So now I need to show this inclusion. So I take an element here, X, and I want to show that it belongs to the union. What does it mean to belong to the union? It means that it belongs to at least one of the factors of the union. Okay, so I took X, and X always belongs to X times H, to the coset of H with respect to X. Because X can be written as X times 1. And 1 is an element in H. H is a subgroup, right? So X, which is X times 1, always belongs to XH. And hence it belongs to the union. Okay? Jan, how do you feel about it?
More or less. Yeah, I think I got some of it. I'm fine with the first obvious one. It's more like the other one. But
yeah, okay, so let me repeat. I mean, I take, how do you prove inclusion of sets? You take an element in the small set, and you show that this element is in the big set. We want to show now the blue direction, right? So I take an element, so I can write it like this. Let X be in G. This is an element in the small set. Since 1 is an element in H, X, which can be written as X times 1, is an element in XH. Because XH, I remind you, is just X times H, where H is taken arbitrarily from the subgroup H. In particular, I can take small h to be 1. So the bottom line is that X is an element in the coset XH. Okay, so if it is an element in one of the group, in one of the sets of the union, then it is an element in the union of sets. So X is in the union of all XH. I guess X here is a bit confusing because and maybe we do it like this. All TH where T is in G. Okay, it just okay, so this is one direction, this is the easy direction. Now, B. We want to show that for any X and Y in G, either XH is equal to YH, or XH intersection YH is the empty set. So there could not be only partial intersection. So suppose XH intersection, suppose XH intersection YH contains an element alpha. Then I can write alpha in two ways, right? I can write alpha as XH, that there exists some H and H prime, such that alpha on the one hand is equal to XH, and on the other hand, it is equal to YH prime. Right? That's what it means to be in a coset. Then I can write X as Y, H prime, H minus 1. And I just multiplied this equation by H minus 1 on the right. And H prime, H minus 1 is in H. Right? This guy is in H. Because H minus 1, I mean, small h to the minus 1 is obviously an element in H, because H is a subgroup. And then because H is a subgroup, you take H prime times H to the minus 1. You get an element in H because H is closed under multiplication. So what I'm saying is that this guy, Y H prime H minus 1, is an element in Y H, in the coset of H with respect to Y. Because I can express it as Y times an element in H. Now I do the same trick for Y. I can express Y as X H H prime to the minus 1. So I conclude that Y is an element in the coset of XH. Now, show that in this case, XH is in fact equal to YH. So the claim, I just reformulated the claim that I need to prove. I mean, if I have one element, alpha, that is common to the two cosets, then they are equal. That's an equivalent claim to what we want. So I have this alpha, and I want to show that XH is equal to YH. Again, equality of sets you prove by a double inclusion. And so here is one direction of inclusion. Let A equals X, I don't know, XS, be an element in XH. Okay? Then X, I have a formula to write X as an element in YH. Right? So I use this formula. I do A is equal to YH prime H minus 1. This is X times S. But by associativity, I can write it as Y H prime H minus 1 times S. And this whole thing is in H. Right? When I say A is equal to XS, it means that S is in H. So altogether, I get that A is an element in YH. You see, I started with a general element in XH, and I conclude that it is in YH. Now I do the same. This is symmetric. So YH is contained in XH. I take B to be YT, a general element in YH. Right? So this, I really mean that T is an element in H. And I have a formula for Y. I have a formula for Y here. So so I plug in this formula. And then B is equal to X H H prime minus 1 times t. But this whole thing is an element in H, because it's a multiplication of elements in H. So this guy is an element in XH. Okay, so now this proves the inclusion in the other direction. So hence, XH is equal to YH. And this ends the proof. Questions before we take a break? All right, let's meet in 10 minutes. Okay, so the picture for the last theorem, let me give an example. We had you pick an integer n, and you consider, I mean, even let's pick a positive integer, and you consider the subgroup of all multiples of n and we saw that this is a subgroup of the group of integers, with addition. And so what this claim, the proposition we proved before the break, it says that if you take the collection of all cosets x plus nz, where you run over all elements in Z, you get the whole thing. But I remind you, we said before the break that this collection of cosets has a lot of repetitions. And we would like to pin down exactly when there is a repetition. This is the following lemma. For H and G as above, I mean, G is a group and H is a subgroup. And, well, and X and Y, some elements in G, XH is equal to YH if and only if XY minus 1 belongs to H. And this is the same as saying that X minus 1 Y belongs to H. Going to be equivalent. Okay, so this lemma characterizes when two cosets are equal. Two cosets are equal if they're representative. This is called a representative. If when you multiply the two representatives, where one representative you take the inverse, you get an element in H. Okay, so how to prove this? Suppose, remember, we have an if and only if. So one direction is if xh is equal to yh, then I want to prove that xy minus 1 is in H. So I assume the two cosets are equal. Since y can be expressed as y times 1, it is in YH. And since the two cosets are equal, then Y must be an element in XH, i.e., there exists some H in H such that y is equal to xh. Right? That's what it means to be in xh. But then we want x, so y x minus 1 is equal to h, and h is an element in h. So y x minus 1 is an element in h. Note also, if you want to do it in the other direction, x is equal to x times 1. So x is always an element in the coset xh. And the coset xh is assumed to be equal to the coset yh. So x must be an element in the coset yh, i.e., there exists some h prime such that x is equal to yh prime. And then x, y minus 1x is equal to h prime, which is an element in h. Okay, so this is it's the same. The whole claim is anyway symmetric, so you can do either y minus 1 or x minus 1y. Doesn't matter. And this proves the first direction. Conversely, suppose x y minus 1 is an element in H, and we want to show that the two cosets are equal. And we to show equality of sets, again, we do double inclusion. So y is equal to x minus 1 y. Okay. So let's suppose x minus 1 y is in H. Then y is equal to x times x minus 1 y. And this guy is assumed to be in H. So y belongs to xh. If y belongs to xh, then it means that xh must be equal to yh. Why? I claim that now that we know that y belongs to xh, to the coset of h with respect to x, I can immediately deduce that xh is equal to yh.
Well, because the partitioning theorem we saw before.
Yes. Two cosets are either equal or disjoint. If one element is in both sets, then they must be equal. Okay, so this proves the lemma. So the lemma again tells us that in order for two cosets to be equal, if you multiply their representatives and you do inverse on one of them, then it must be in the sum. It's an equivalent condition of when the two cosets are equal. And just as a remark, if alpha is equal to xh, well, if alpha belongs to the coset xh, then alpha is equal to xh, or some h, but I claim that there is a unique age in age. So you can express alpha uniquely as a product of x with an element in h.
But that means the coset is not in the case we were talking about. Like with the lines of the plane, if the base group, or I don't know how you call it, the group,
the ambient or the sub,
the subgroup that we use to create all the coset, this one is also considered as a coset. In that case, it can not be uniquely, because
if the x is not unique, but once you choose x, so if you fix an x,
okay.
If you fix an x, then alpha is equal, so for fixed x, if you get an element in the coset, then it is uniquely expressed as x times h. Why? If you can write alpha as xh on one hand, and alpha as xh prime on the other hand, then I can multiply all this equation on the left by x minus 1. And what I get is that x minus 1 xh prime is equal to x minus 1 xh. This is the same as saying that h prime is equal to h. Okay, so you cannot do, I mean, this, there exists an age, but this age is unique. Now, fix x and y, and define a function f from the coset of age with respect to x to the coset of y of age with respect to y. By what do I do? Well, f, I plug in some xh and I map it into yh. Okay, this function is well defined because of the remark. Because I know that every element in the coset xh has a unique representation as x small h, and I take this representation and I map it into another unique representation yh. Now I claim, okay, f is clearly surjective. Right? Because every element in the coset yh is being hit by some, I mean, by an output of the function f. Right? I mean, the function f covers all the range, all the target coset yh. Okay, take an element in the target set y age. How does it look like? It looks like y times small h. Okay, if beta is an element in y age, then there exists some age in age such that beta is equal to y age. And then f of x age with this particular age will be y age, which is beta. Okay? So this is clearly surjective. I claim that this is also injective. Over f is injective. What do I need to show in order to prove that f is injective? I take two elements in the domain set, two elements that are different, and I need to show that f maps them to different outputs, different elements in the target. If I have let's say alpha and alpha prime, alpha prime in the domain, with, let's say, alpha is x age and alpha prime is x age prime. Then f of alpha, well, let's put it like this. If f of alpha is equal to f of alpha prime, then I just, by definition of f, it means that y age is equal to y h prime. Right? Because f alpha is x age, so f maps x age to y age. And alpha prime is x h prime, so f maps alpha prime into y h prime. If these two are equal, then it means that y age is equal to y h prime. But then I multiply all this equation on the left by y minus 1. I get that age is equal to h prime, and therefore alpha is equal to alpha prime. Because the representation is unique. Okay, so what I get is, to sum up, the function f from x age to y age that takes an element alpha and maps it into, say, f of alpha is bijective. This is without any assumption that age and g are finite. This is always bijective function. But in case g and age are finite, bijective means that the two sets have the same number of elements, right? So, now suppose g is finite. Then this discussion says that the number of elements in x age is equal to the number of elements in y age for any x, y in g. Right? This is what we just proved. And so G can be partitioned into sets of equal size. How many of them? I don't know, because there is a repetition. And I have a condition to pin down when a repetition happens, but I don't know exactly how to count how many repetitions. But either way, I get a famous theorem by Lagrange. This is Lagrange. And Lagrange says if G is a finite group, and H is a subgroup, then the number of elements in H must divide the number of elements in G. And the proof is basically the discussion we had. Because if I can partition G into sets of equal size, what is the size of xh? The size of xh for any x is the size of h. H is also in this partition. Maybe I add it into the equal size. The size is equal to, for example, the coset 1 times h. The coset 1 times h is simply the subgroup h. Okay? So in the proof is what we, G is equal to the union of all xh, x in G, and as a partition, and the number of elements in xh for any x the number of elements in xh has to be equal to the number of elements in the coset 1 times h, which is the number of elements in h. So I get that x is partitioned to sets of equal size. Each of them is of size, the size of h. Okay, so the number of elements in G is just a multiple of the number of elements in G. H.
Yeah, maybe it's me over-interpreting the complexity of the last, not the Lagrange, but everything that came before, but just the fact that we have, for every alpha, there will be a unique H in capital H to define it. Doesn't that already say it's a bijection, and therefore every don't you get that more faster?
You get it more faster if I was just I was explaining stuff that are usually referred to as trivial details.
Right.
But again, it depends on your background. I mean, if you didn't see the material before, what I call trivial is not immediate.
Right.
So I just explain all the details.
Yeah. Okay. Yeah. I mean, it's in hindsight, first of all.
Yeah. I mean, but to to show that something is bijective, you need. I mean, I break it up to all the pieces. You need to show surjective. You need to show injective.
Yeah.
Injective, basically, I mean, injectivity is completely equivalent to the unique representation.
Yeah.
Surjectivity is immediate.
Mm-hmm.
Okay, so you get bijective.
Right.
Yeah.
Right. Yeah. Okay. Yeah.
Okay, so this is one dividend we can draw from the this proposition, the fact that we have a partition. But there is another thing that we can conclude from the partition. I remind you that when we talked about equivalence relations, we said that one one equivalent way to show, to talk about equivalence relation is to talk about partitions. If I have a set, so we call, or a set S, a relation tilde on S is an equivalence relation if and only if we can partition S to the equivalence classes of the elements in S. So I write it like this: union of all brackets S, S is in S. Just to give you one example, I mean, you take the equivalence relation on S equals Z, and you take the relation tilde to be A is equivalent to B if and only if A is equal to B modulo N. This is an equivalence relation, right? And what is the equivalence class of A? The equivalence class of A is, by definition, it's A is the set of all, let's say, X in Z, such that A is equivalent to X. And the equivalence class is all the guys that are equivalent to you. And to write it more concretely, in our case, it means all the X in Z such that X is equal to A modulo N. And if you, so this is the equivalence class of A. If you now run over all A in Z, you get a partition. Because, I mean, the equivalence, actually, you have the equivalence class of 0. This would be 0, n, minus n also, 2n, minus 2n, and so on. You have the equivalence class of 1. It will be 1, n plus 1, minus n plus 1, and so on. And you have the equivalence class up to the equivalence class of n minus 1, because the equivalence class of n is going to be equal to the equivalence class of 0. So you see, this is a partition of the integers. I mean, the collection of all equivalence classes or if you wish, it's the same as the collection of all equivalence classes where I run over all elements in Z. This is a partition of Z, right? I mean, I take Z. Z is all the dots on the line of numbers. And here I will have, let's say, 0. And here, so it will be 0. And let's say n is equal to 3. So I have, in the same equivalence class of 0, I have 3 and some other guys. And then a second equivalence class would be the equivalence class of 1. It would be 1, 4, and so on. And the third would be the orange guy, and 2. So you take all equivalence classes, you get a partition of the set. This is true for any equivalence relation. It's in fact it's an equivalent definition of an equivalence relation. I just as you give me a partition, I mean, if let's say S is equal to S I is in some index set, and Si is a partition of S. That is, I remind you, for any I and J in the index set, either Si is equal to Sj, or Si intersection Sj is the empty set. If I have such a partition, I can define an equivalence relation tilde on S by setting X equivalent to Y if and only if there exists some I such that X and Y are elements in Si. Okay, so this is the other direction. You give me a partition of the integers, for example, then I can define an equivalence relation by this partition. So if you take this partition, for example, you take this partition of the integers, then I say the two elements are equivalent if they belong to one set of the partition, and this would be the same as saying that two elements are equivalent if they are equal modulo n. But coming back to the theorem, I mean, we had the partition, and so for two subgroups, we have a partition of G by the collection of cosets. Xh, X is in G. And this partition defines an equivalence relation.
Sorry, just need to take something.
So the equivalence relation is I take alpha and beta in G, and I say that alpha is equivalent to beta if and only if alpha and beta belong to the same coset. For some x. Of course, if they belong to one coset, they cannot belong to another coset because the cosets are either equal or disjoint. And so if I have an equivalence relation, I can take the quotient. The quotient is taking all the equivalence classes of element. The equivalence class of alpha, in this case, the equivalence class of alpha, which I remind you, it's all the beta in G, such that alpha is equivalent to beta. But I defined alpha equivalent to beta if and only if they belong to the same coset. So the equivalence class of alpha is simply the coset XH. Okay? Then G modulo. Remember, when we talked about equivalence relation, we talked about the quotient of a set by an equivalence relation. This, by definition, it's the set of all equivalence classes. But in our case, it's simply the set of all cosets. Definition. The quotient of G by H is this guy, G mod H. I define it to be the quotient of G by the equivalence relation coming from the cosets, all the cosets of H. I.e., this is just the quotient on in plain words is simply the collection of all cosets. Okay. But I wanted to explain it from the view of equivalence relations to justify the terminology. And quotient really means here that we quotient by an equivalence relation that is canonically obtained from the subgroup H. I take all the translations of the subgroup H by elements. This is the cosets. And this gives me a partition, hence an equivalence relation, and I mod out. I think this is a good place to stop. I mean, of course, I can define a group. I mean, the next thing would be to define a group structure on the quotient set. But just to wrap it in examples. An example, let's say G is the integers, and H is multiples of a particular natural number n. Then G mod H is it's the collection of all cosets. So this is the coset of 0, coset of 1, up to the coset of n minus 1. Of course, I can write cosets of other integers, but this would be repeating. the cosets written in this list. Okay, so you see there is a group structure, a natural group structure that we know on this quotient, because I mean, if you want to, the operation here is addition, right? So I just, in the quotient group, in the quotient set, the operation I can take is addition modulo n. So 0, or I don't know, A plus B would be the coset of A plus B modulo n. Okay? And in fact, this is generally true if H is abelian. So this is generally one can define canonical group structure canonical, I mean really induced from G from G and H. On the quotient set G modulo H, if H is abelian, or if G is abelian. Okay, this something you can look in the notes, and of course we will cover it eventually if we get to it. But it's a good place to stop, I think. All right. Questions on this?
Yes, it's pretty stupid as a question, but why do you say G modulo H instead of G quotient H?
This modulo and quotient for me is synonym.
Synonym, is it? Yeah.
To mod out is to.
Right. Yes. Okay.
Okay. So I hope we can get more people. I will write something on Discord. Maybe if some of you, if any of you know other people that want to be, might be interested in joining, either let me know directly or post something on Discord. We'll try to collect a group.
You can announce on the theory meetup.
Sorry?
There is a theory meetup at some point soon. We would announce there for this one. Yeah, you can talk to our front guest. She organized it.
Yeah. Okay, I'll just end the call.